So this is your E&M physics lecture coming to you live from the basement of Markle. This is the situation we're in right now. We're going to pick up exactly where we left off. We're going to start in on chapter 31, which begins with the discussion of LC oscillations, that's inductor capacitor oscillations. We then moved on to damped LC circuits, and then we start talking about AC circuits, alternating current circuits. Best thing for you guys to do, I'm going to try to keep these videos short, less than 10 minutes each one. If I need another whiteboard, I have another one underneath here. Feel free to pause when you're writing down for your notes or that sort of thing. Okay, so what are we talking about in LC oscillations? We're talking about an inductor and we're talking about a capacitor. Now we already know what these two things do. They store energy. The inductor stores energy inside of the magnetic field that's created in the inductor, and the capacitor stores energy in the electric field inside of the capacitor. So these two things are going to be storing energy. If you look, and I'm going to be going back and forth off screen a little bit to get my notes, if you look on page 827, you will actually see an example, and what you see is that we oscillate back and forth between the maximum energy being in the inductor and then the maximum energy being in the capacitor. That's because we know that the inductor is going to induce a current that is going to oppose the flux change. If you forget that stuff, go back to the previous chapter. So the energy inside of the electric field, UE, that's the energy, potential energy inside of the electric field, and the electric field means that we're referring to the capacitor. That amount of energy is going to be equal to Q squared over 2C. So that's charge squared divided by 2 times the capacitance. This is the energy stored inside of the capacitor. The energy stored inside of the inductor will be the potential energy of the magnetic field. So UB is going to be equal to Li squared divided by 2. So that's the inductance multiplied by the current squared divided by 2. So once again, energy inside of the capacitor, energy inside of the inductor. Okay? Now, as we deal with this sort of thing, since we're going to be oscillating back and forth, we're going to A, treat it as oscillations, and B, that means we have to refer to everything as an amplitude. If you remember back to mechanics last year, the first time you studied physics, we talked about a spring and a mass, and the mass moving back and forth on a spring. We referred to the amplitude of the displacement as far out as the mass could get from the equilibrium position, either through a stretch or through a compression. We're going to use the exact same idea here. So little q is going to refer to the charge at a certain amount of time. Big Q will refer to the amplitude of the charge. So that'll be the maximum amount of charge. So you just want to kind of keep that in mind real quick. Okay. Now to make things a little bit easier, we're going to make an oscillation analog. So we're going to make an analog to something that we've done before in order to better understand what's going on. Again, the key idea here is that all the energy is going to be on the inductor, and then all the energy is going to transfer to the capacitor, and then all the energy is going to go back to the inductor. That's the oscillation back and forth. Okay? So this is the electrical, mechanical analogy. Mechanical analogy. I'm still getting used to writing on this. I wish I was in my classroom, but what are you going to do? Okay? So we're going to have two systems. We're going to have the spring block system, and we're going to have the LC oscillator. Okay? So our spring block system is going to be over here. This is our spring block. And then over here, we're going to have our LC oscillator. Okay? Now, if we go back to the spring block system, so this is all the way from last year, we know that the potential energy is going to be stored inside the spring. So the potential energy is 1/2 kx squared. 1/2 kx squared. The kinetic energy is in the block as it's moving back and forth. So that kinetic energy is 1/2 mv squared. 1/2 mv squared. Okay? And then we know that the velocity is equal to dx dt. Velocity is equal to dx dt, taking the time derivative of the position. Okay? Our energy inside of the capacitor is the electric field energy. That's going to be equal to, remind myself over here, 1/2. And I'm going to write it a little weird. I'm going to write 1/c and then q squared. I'm going to try to keep this from falling down. Okay, so this is 1/2 1 over c times q squared. Now notice what we're doing here. We're setting it up to look like the spring block system from before, from last year. So I've got the 1/2, similar to the potential energy. The k constant is going to be like 1 over c, and then x squared, the displacement squared, is going to be our analog to the charge squared. Okay, so that's why I wrote it like that. Now we're going to make the kinetic energy sort of like the energy in the magnetic field, and that's going to be 1/2 L times I squared. So the inductor is kind of like the mass, and the current is kind of like the velocity. Yes, if you're thinking ahead, we're already going to be going to sine and cosines here in a couple minutes. And then we remind ourselves that I is equal to dq dt. So the change in charge with respect to time. Get these in your notes. Pause the video right now if you want to get these into your notes, because I'm going to have to go on to the next whiteboard. Okay? So I have set up my analogy right here to electrical, mechanical. That made a big sound, more than I was expecting. Okay, so the k constant is going to be like 1 over c. X is going to be like q. This is just me repeating everything I did before. Dx dt is going to be like dq dt. Okay, so the velocity is going to be like the current. Okay, the mass is going to be like the inductor. Mass is going to be like the inductor. So these are all the analogs that we went over on the last page. Okay? We remind ourselves that we had an angular frequency for the spring block system. Can anybody remember what it was? I'm going to assume you don't remember. That's okay, I don't remember either. The angular frequency was the square root of k over m. So this was for our spring block system. The angular frequency, omega, was the square root of the spring constant divided by the mass. Now, since the spring constant is basically going to be 1 over c, and the mass is going to be the inductor, I'm now going to create something that is an angular frequency for this LC circuit. So the angular frequency of my LC circuit is going to be the square root of 1 over LC. Okay? This was for the spring block system. This is for our LC circuit. Okay? Now, we're going to use energy conservation to handle this whole thing. Okay? We know what the total energy should be in our system. The energy is going to be split up between the inductor and the capacitor. So U total, the total amount of energy, is going to be equal to UE plus UB. Okay? The energy on the capacitor plus the energy in the inductor is equal to the total energy. Okay? So that is going to be rewritten as U total is equal to I should keep everything in order just to make my life easier. Li squared over 2. So that's the energy inside the inductor, plus the energy inside the capacitor, which is Q squared over 2C. Okay? Now, I'm going to do something crazy here. I'm going to take the time derivative of the energy. Okay? Watch what's going to happen here. I'm going to take the time derivative of the energy. And remember, this is not intuitive while we're doing this. So don't stress too much if it seems a little weird while we're doing it. So du dt is going to be equal to the time derivative of Li squared over 2 plus Q squared over 2C. Okay? Make your notes look a little bit better. Okay? I think I need to get a third whiteboard. Okay. So when I take the time derivative of this, I'm going to have du dt is equal to, take the time derivative of the current right here, and I'm going to write it in kind of a unique way. So when I take the time derivative of the current, the 2 is going to come down in front, it's going to cancel out the 2. We assume that the inductance is not changing in time, but then I'm going to have Li di dt. There's a reason why I'm doing that, so keep that in mind for a second. Then we're going to take the derivative of, over here, the energy on the capacitor. That's going to be plus Q over C dQ dt. So once again, the 2 has come down in front, canceled out the 2 in the denominator. I'm taking the derivative of the charge inside of there. Okay? Now, when I manipulate this thing a little bit, we know what dq dt is. That's the current. So this has a current term here, this has a current term here. I'm going to rip the currents out of both of them. So the current is equal to the inductance, di dt, plus Q over C. Okay, I have just enough space to finish up. Okay, so what I have here is I have a differential equation that I'm going to need to solve. Okay, I have some kind of differential equation that I'm going to need to solve. We assume that no energy is lost. So if no energy is lost, what's du dt going to be? It's going to be 0. So that means I've got 0 is equal to L di dt, plus Q over C. And now di dt can be written as the second derivative of the charge with respect to time. And I've got U is equal to L d squared Q dt squared plus Q over C. Okay? So this is my differential equation. This step right here, I went a little fast on this. Let me explain it again. You're taking the time derivative of the current, but you already know that the current is equal to the first derivative of the charge. So taking the derivative again, that's why you have the second derivative of the charge right there. This is my differential equation, okay? So we want to solve this thing right now. And if you solve it, you're going to get that the charge is equal to some charge amplitude Q cosine of omega t plus phi. So this is the charge as some function of time is equal to capital Q, that represents the amplitude of the charge, cosine omega t plus phi. Omega is our angular frequency term that we defined over here for the LC circuit. When we take the time derivative of this, we're going to get the current as a function of time. So the current is the time derivative of this guy. Notice that you're going to take the derivative of cosines. That's going to give us a minus sign out front. And that's also going to give us an omega term out front. So it's going to be minus Q omega sine of omega t plus phi. Okay? So that's my charge as a function of time. That's my current as a function of time. Okay? You can then rewrite the energy for both of these guys. You can rewrite the energy, and I'll probably put that in the next video, and I'll talk about the damped oscillations, so I keep this video fairly short. So I'm going to rewrite the energy in the next video, and then I'm going to talk about damped LC oscillations. Okay? Again, make sure to pause the video and write things down if you need to.